Yeah, we're gonna do a classic math problem for the very first. The very first problem that we're gonna do is a classic problem. Maybe you've seen it before. It goes something like this. Okay, it's a pretend you're on a game show. Okay, and there are 3 doors. This is door number 1. This is door number 2. This is door number 3. This is very, very classic. Okay, 3 doors. Okay. Okay. A great prize is behind door number 1, door number 2, or door number 3. You let's say you have chosen. Okay. You think that the great prize is behind door number 1. That's the one that you chose. Okay. I then proceed to open door number 2 and show you that there is a rubber chicken inside. Then this is my drawing of a rubber chicken. And no, it's not a prize. It's supposed to be like a gag gift, okay? So you chose door number 1. I open door number 2 and I say, behind door number 2 there's a rubber chicken, which is not the great prize, by the way, okay? So the question is, would you or should you stay with should you stay with door number 1, or should you switch your guess to door number 2? All right, think about it for a second. Talk to somebody who's sitting right next to you. Did I just say it wrong? Okay. Oh, did I say it wrong? Sorry. Let me say it again. I meant 3. Yeah. So you chose door number 1. You think the great prize is behind door number 1. Sorry. I opened door number 2, and there's a rubber chicken behind there, and so you don't want that one. So the question is whether or not you switch to door number 3. Excuse me. Or you stay with door number 1. Talk with your partner, the same person you worked with right now. Okay. So you've had a chance to talk about it. This was actually in a movie. I think it was. We talked about it last class. Was it 21? The movie 21? Yeah. Okay. This is actually a new. Okay. All right. So the one with the count cards. Yeah. So what do you guys think? Should you switch or should you not switch? You should switch. Okay. Who? One says don't switch. Who can explain why you think you should switch? Yeah. Cole, go for it. What do you think?
Let's say you picked door number 1. Let's say you haven't picked anything yet. There is a 1/3 chance that it is behind door number 1, 1/3 that is behind door number 2, and 1/3 that is behind door number 3.
Okay, so if you don't know anything, you have 1/3, you have 1/3, you have 1/3 of getting it correct. Is that true?
So now, if you've chosen door 1 but he hasn't revealed anything, there is a 1/3 chance you got it right and a 2/3 chance that you've got it wrong.
Everybody agree so far? So without looking at any doors, the very first guess that you try, you have a 1/3 chance or probability of getting it correct, and 2/3 of getting it wrong.
Which means there is a 2/3 chance that it is behind either 2 or 3.
Does that make sense?
Yeah.
Okay, so 2/3 chance is behind the other one. Okay.
Now that he's revealed 2,
Yep.
there is a 1/3 chance that it's behind door number 1, but there is a 2/3 chance that it's behind door number 3.
Yeah, so since you know it's not this one anymore, this one now changes to 2/3 that you chose incorrectly the first time, right?
Wait, no, but then it just depends on which one your reveal space.
No, it works the same way, okay? He's on the right, you have a very good explanation, and I'm with you, but still people are like, many people are confused about this one.
Not revealed the correct one.
Yeah, he's not going to reveal the correct one, obviously, right? Okay. Let me break it down for you a different way, okay? The answer is that you should switch, and here's why, all right? When you first start, okay, what's the probability that you actually pick the right door? You have a 1/3 chance that you get it correct. Do you guys agree with that? That means you have a 2/3 chance you get it wrong. You agree with that? So what are you more likely to do more often? Get it right or get it wrong? You're more likely to get it wrong because there's 2/3 chance, okay?
Oh, so then when your gut instinct was 1.
Exactly. So if you are 66% of the time going to get this wrong based off of this number, right? So assuming you go with that, assuming you did get it wrong, which you will. Now it won't work all the time, right? But you have a higher percentage of chance of switching because you're now basing your second guess off the fact that one of your choices has been eliminated for you. So now your next guess is not based off a third, and a third, right? It's different. What has happened is your sample space has changed because we've taken an option away.
But would it just be half chance and half chance?
No, it's not half chance and half chance because the original door you picked was based off of thirds, not a half.
But what if you picked 3 first?
Doesn't matter. If you picked 3 first, okay, you would still switch. Now, it's not guaranteed. It's the same logic in reverse. Okay, I chose door number 3. I showed you door number 2. You should still switch, right?
Yeah, but I don't understand why.
This is why.
I know, but I don't understand that.
What we eventually are talking about here is something that's called conditional probability. All right, so let's define conditional probability. It's going to be defined as this. So the probability of event B will occur given event A.
What does that say, B?
Yeah, that's a B, sorry. That's not very clear. Okay, so the definition for a conditional probability is as such. The probability that B will occur given that event A has already occurred. Okay, so that's our definition. That's what it means to have a conditional probability. We are wondering, how does our sample space change given the fact that something else has already occurred, okay? So how do we write this in mathematical language? This is what we say. This says the probability of the probability of B given A has already occurred. This is how we write it. So these are parentheses. I didn't do a very good job with that. And the B and the A are the 2 events. The line in the middle says that you have been given event A. So the way that you would read this is the probability of event B given event A has already happened. So given event A. All right, that's how we read it. So this is what we're going to be working with for the majority of the day. Probability of event B given event A has already happened. Okay, let me explain what this table represents. So I'm comparing males and females with 3 types of colleges. There's a 2-year college, there's a 4-year college, and then there's grad school. So basically, junior college versus like a university, and then versus like a graduate school, okay? These are all the numbers that represent the students that go to a particular university, either 2-year, 4-year, or graduate school, male and female, right? And we're interested in a couple of things. We want to explore this concept. So I'm interested in what's the probability that I would choose if I'm choosing a person random or female, given that they are in graduate school. Okay? So probability of choosing a female given that they're in graduate school. Okay, so our sample space has now been reduced. Our sample space is not everybody. It's only restricted to what? People who are in what? Graduate school. So this answer, I'm going to move this over to the side so we can still see. This answer is still calculated by a fraction because it's probability, right? So the sample space is going to be the easier of them to figure out. That is the total in where? Yeah, the total in graduate school. Doesn't that make sense? Okay. My sample space is just based on what I'm looking at because I have been given that the graduate school has occurred. Okay, so my bottom is going to be total in graduate school. My numerator is going to be the number of favorable outcomes. So what am I looking for? I'm looking for females, right? So I want females, but they have to be where? Females and in grad school. Okay, am I breaking this down for you enough? Does it make sense? So I'm comparing, probability is, theoretical probability, favorable over total, but my sample space has been restricted to a certain location because I have been given the fact that graduate school has occurred. I'm picking from graduate school. Okay, great. So now we can actually compute this probability. So what number represents females and in graduate school? Yeah, that'd be that one, right? So 1954. And then total in graduate school, well, it would be the sum of these two added together, wouldn't it? So 3,3303, right? Okay. So that is approximately like 59% when I calculated that out. What's the difference between theoretical probability and conditional probability, right? What's the condition? What has changed? your sample space has been restricted. Right? In this case, our sample space was restricted to what? Yeah, total in grad school, okay? It's not that big of a concept, but it's if you don't understand what you're writing down and why you're writing it down, then it's no good. Okay, let's stay in this one since we set this table. What's the probability of picking a 4-year student given that it's male? Okay, so probability to randomly pick a student given that, or probability of getting a 4-year student given already that a person is male, okay? So let's talk about our sample space. What would our sample space be? Yeah, the males, right? So the total males. Because our sample space is restricted to only males, right? What would the top be? Yeah, I'm going to erase all these. So male and what? Yeah, these are my favorable outcomes, right? Male and in 4 years, right? Okay, so now let's compute that probability. Male and 4-year, what number is represented by that? That's this number here, right? That would be 4, 3, 2, 4. Total males would be this one plus the middle one plus the last one. If you add those all up, what do you get? 7,539. You're absolutely correct. So if we compute this, I'm looking at like, yeah, what'd you get? Can you help me out there? 57%. Okay, so here's the setup for the example for the U-try. So there are a bunch of materials here: paper, metal, glass, plastic, and others. And they're measured in millions of tons in the year 2007. So I just basically have some stats here for you. Okay. So there were 45.2 million tons of paper that was recycled, and there were 37.8 million tons of paper that was not recycled in the year 2007. So there's all the backstory. Okay. I'd like you to compute the following. Right. The probability that probability that you chose paper, given that it was recycled as a sample, right? And then similarly, probability plastic, given that it was recycled, and then similarly, probability glass, given that it was recycled. Recycle. Okay, here we go. Let's check our work here. For part A, a probability that a sample is that was paper, given that it was recycled. What'd you guys do? Like, what'd you set up?
This is always the safest number.
Okay, so it is a fraction, right? What's your bottom number? Total recycled. Nice job. Total recycled. Okay. And then what's your top number? Paper recycled, right? Paper and recycled. Paper and recycled. I'm getting kind of hard to see here. Okay, so how much is paper and recycled? That number is characterized by what? By the 45.2. Does everyone go with that part? Okay, what's the total recycled? Well, isn't it just
79.
yeah, all of these added up together? So 79.7, is that what I got? 79.4? Okay, good. So what'd you guys get for about a percentage for this one? About 56 point something, about 57%. Okay, I'm with you on that one. Okay, similarly, what'd you guys get for plastic? 3%? I got 2.64. I got approximately 2.64%. You guys just got rounded up, okay? How about for glass, what'd you guys get? I got, 4.03%. Did everyone in the room get the same thing? Is anyone in the room not sure about how to get that? Okay, we're all good. Sweet. All right, I want to do this example. It's a tree diagram example. There's a lot of words to it, so I'm going to read the example to you, and we'll write down the important information, okay? Reading the example to you. Here it is, right here. It says, a school system compiled the following information from a survey that it sent out to people who were juniors 10 years earlier. Okay, so people were juniors 10 years earlier. It says 85% of the students graduated from high school. All right, that's pretty good. So 85%. We're going to write down the good information. Graduated. All right, cool. Got it. Of the students who graduated from high school, 90% were happy with their present job. So underneath this category, we had 90% were happy with their present job. Okay, good. The other information that we have is this. Of the students who did not graduate, so not graduate, those guys are over here, not graduates, 60% were happy with their present job. So underneath this category, we had 60% that were happy with their present job. And the question is, what's the probability that a person from the class graduated from high school and is happy with their present job? Okay? Yeah, exactly. You're on the right track, okay? So well, you're going to have to make a diagram, a tree diagram, to represent all of the data, okay? So let's start off by making our two choices. The first two choices that we have to decide are whether or not they graduated, right? So we'll say graduate, not graduate, okay? How many people, what percentage of the people graduated? Okay, so this is 0.85, right? Everyone okay where that number comes from? Okay. Well, if 0.85 graduated, then how many didn't graduate? 0.15 didn't graduate. Okay, so far so good. Now we have to break off into our second branch, right? Of those who graduated, we also know a little bit more, right? How many were, they're either going to be happy or not so happy, right? And then likewise over here, happy and not happy. Okay. Of those who graduated, what do we know? 90% of them are happy. So this is 0.9. So how many are not happy? 0.1. What's our, for the not, and then 60% were happy. So 0.6, that means how many were not happy? 0.4. Okay. And we want to know this, okay? We want to know what's the probability of graduated and happy. Okay? Well, and means multiply, right? Yeah, so we're going to do the probability of graduated multiplied by the probability of happy. Or I like how Rachel phrased it. You said 90% of the 85. Does that make sense? 90% of the 85. So we're going to take this number, we're going to multiply it by that number. Right? That's 90% of the 85 who graduated. So that's going to be 0.9 times 0.85. And that's going to give us a grand total of what? 0.765, or how can we say that? 76.5% around that if I go to one decimal place, okay? Okay, I'm going to do, for the last box in the lesson, I want to actually do number 30 from your homework, okay? There you go. So number 30 gives you a diagram, okay? And it looks like this right here, okay? So I'll tell you what each of these things mean once you read it. Or I'll stay with black for now. So this is an H, this is an L, this is a C, this is an O, this is a C, and this is an O. So the H and the L stand for heavy snowfall and light snowfall. And the O and the C stand for whether or not school is open. Okay? So you can see heavy and closed, heavy and open, light and closed, light and open, okay? And then they give you some probabilities that they fill in. They say probability of heavy snow is 0.4. Probability of light snow is 0.6. They give you probability of heavy and then closed 0.8, 0.2. Okay? Probability of light and closed is 0.3, and then 0.7. Okay? So this chart is given to you in number 6. In number 30 of, this is my box 6 of the lesson, okay? And then number 30 is asking you for this. What's the probability of light snow given closed? Okay? Given closed. So, the way we'd figure it out is, okay, what's our sample space, right? Our sample space is closed, right? What's the probability of something being closed?
0.7.
No, closed, right? It's either closed or open, right? This is closed or open. I only have 2 of 4, right? So it's a half. So it's a half down here, okay? Because, look, I have a C, an O, a C, or an O. I have 2 C's and I have 2 O's. That's why it's a half, okay? Does that make sense? Got it? Okay, good. Now, probability of L given C means what's the probability of L and C happening together, right? So L and C happening together. 0.18, exactly. So that's 0.6, right? Yeah, times 0.3 divided by 0.5. So that's 0.18 divided by 0.5, which is 0.36, 36%. Okay? It's a tough question. I wanted to give you guys a heads